Okay, this video is going to be a continuation of the last video on binary trees. And this is just a very basic introduction with binary trees. Last time we created a binary tree that sort of took this form. We have the concept of a node that stores a value. So node is just sort of an abstract term. I mean, it's basically a box. It's a storage device, something that stores some value. And so you have the concept of a root node. Right, that's the beginning of the tree. That's the root of the tree. Now, every node has the option to have children, and since this is a binary tree, we can say it has two children, a left child or a right child. You could also number those children if you want. You could say child 0 and child 1. You could give them any sort of criteria to name them, but it's just common to say left and right since there's two. All right, and so we tried to figure out a way to create this structure using the programming structures that we're aware of so far, very basic. We used, in the last episode, we used the list. So we had tree data, and tree data was just a list of numbers at first, and at the very end we switched it over to be a list of letters. Right, so what we want to do here is we'll just run what we did last time. Right, this is the bin tree list. Okay, so this is actually how our data was stored in a Python 3 list data structure. Okay, this time we're going to create our own data structure and store the data in an actual sort of binary tree data structure in which we can directly access the left child or the right child by reference of any given node. So what I mean by that is that if we have access to this particular node, if we have a variable that's storing the memory location of this node, I can use that to access the left node. So this will have a left property that will point to the memory location for this node. This node will have a left property pointing to the memory location that holds this node, etc. So there's a left and right property on every node that points to another node, or references, right? So well, that's what we're going to be trying to do, and we're going to recreate the breadth first traversal and the depth first traversals with this new data structure. Again, so we're not going to rely on the list data structure in Python 3. We're going to use a node style data structure. All right, so let's get started. Let's call this bin tree underscore node .py. Alright, and then as you watch the last video, again, I've made this sort of print function that allows us to print out the various types of data structures, these binary tree structures that we're creating. This first one was for the list-based binary tree, and I have a second one here for the node-based binary tree. And again, forgive me, it's kind of messy and it's not necessarily efficient because I've just been copying around and tweaking it to get it to work in different situations. It's been a while since I've really looked at it in depth. But anyway, this is, you can pause your video, and this is the one we're going to be using. This is the print node tree. Now, again, this is a recursive function. We saw last time we used a recursive function, but we had this wrapper function around it. So this is a common strategy. You have an initializer. It initializes the first recursive function. The problem with a recursive function is you can't do something at the very beginning or the very end of a recursive function because it gets called so many times. Right? If you put something at the very beginning of this function, every single time you call it, it's going to do that thing. Right? And there are some ways around that, but it's really common to just add a wrapper function. Right, so that way we can, print something out beforehand and then call our initial recursive function call. All right, so just pointing that again because we had that come up in our last episode there. So this is how to print the node tree. You can pause it and copy that down. There's really not that much different from this one. The only difference really is that data list was a list, and so we had to use square brackets, and then here we have a tree, and so instead of using square brackets we say tree.get. So that just means we need, in order to print one of our trees, we have to add a get method to it in order for this to work. Right? So that's it. You can look this over, you can pause it if you need to and copy this down. I'll try to add this code in the comments. All right, so back to bin tree node. We want to let's see, from bin tree print, we want to import print node tree. Right, and eventually we're gonna use that. And then if name equals main, this is where we basically, you know, test our code. Now the reason we're doing this is because let's see, print. All right. The reason we're doing it like this is because usually when you make classes, you're making classes in a file, and that file is going to be imported in other programs, right? So it's sort of like a library. This will allow us to test the class implementation, but when you import the code into another library, it won't run the tests, right? So name is whenever you run a file directly, this variable name in Python, this built-in variable name is set to this value. And that's only when the file itself is run directly. If I import a file, this will be something else. All right, so what do we want to do here for bin tree node? All right, so first things first is we want to have this concept of a class that is a node. So we define the init function, right, which is the initializer. It's very similar to a constructor in other languages, right? And any of the methods that we create here in a class, we want to include self. Self refers to the object itself, the object being created. So anytime we call this node function, a new object gets created, and self applies to that specific object, not all of the objects, just one specific object at any given time. All right, so define init, and we're also going to pass in some value, because the whole point of the node is to store some value. So we have self.value, and we're going to set that equal to val. And then each node also has a concept of a left and right child. So we look at this tree, you know, the value is 0, but if I want to go to the left child, I would call node.left or self.left, and that should point to a memory location holding this node. Or node.right would point to a memory location holding this node. So initially, we have self.left, and that's just going to equal none, because we don't have any nodes to point. We don't know how to hook them up, how to wire them up. So we just leave them blank to start with, and self.right is going to equal none. And that's really it for the node class. And we can test out what we have here. We can say the root node is node, and we can say that's value 0. And then we could say node 1 is node 1, node 2 equals node 2. And then we could connect these ourselves manually, right? We could say root.left is going to equal node 1, and then root.right is going to equal node 2. And we should probably just add one more node just so we get a sense of this. N3 equals third node. So where would this third node go? Well, in our visual, this is the root node. We have node 1, node 2, node 3. So I'm going to have to set my root node dot left and its dot left property equal to node 3. So here we're sort of wiring these up manually. Okay, so this is going to be root dot left equals n3. And so now the root, if we have root, then we have a connection to all of the other nodes from root. So root.left will get us to node 1, root.right will get us to node 2, root.left or .left will get us to node 3. And we can sort of verify that here by printing out root.value, and root.left.value, root.right.value, root.left.left.value. All right, and that should give us the value 0, 1, 2, and 3. And again, we're wiring this up manually. Ideally, we're going to have a system to wire these up for us. So this is Python 3, bin tree node. All right, running tests 0, 1, 2, 3. So we can sort of see this sort of proves that we do indeed have this structure. Now, I mentioned before that there's a couple things we need in order to have a tree structure, to use our print node tree, right? So one of the things is we're going to have this idea of a tree class. We're going to need this tree class to have an initializer, and it's going to have a self property in there. Don't forget that. Self.root is going to be the root of this tree, but initially when we create a tree there is no root, and so it's also going to have a length, and that's how many nodes are in the tree. Self.length, and we're going to set that equal to 0. So that is the initial things for a tree. So what I could do here is I could create a tree, and since I'm doing all this stuff manually, I would have to say, actually let's do it below. I'm going to create a tree, and I'm going to say tree.root is going to equal this root node, right? But I also have to keep track of the nodes manually, the length, right? So I'll say tree.length equals 4. All right, so now I can do something like print tree.root.left.value. Okay, so as we're using these dot accessors, it's important to remember tree is just a variable. All it holds is a memory location. There's some blob of binary data in memory. Tree is just the name for that numeric address. So when I reference this in Python, Python grabs that memory location, looks for that blob of binary data, it retrieves it, and it's this tree object. I use the dot operator again, and that accesses one of the named properties on that blob of binary data. One of those named properties is root. It's also just like a variable. It's just referencing a memory address. That memory address, when I reference this in Python, it looks up that memory address and finds the blob of data associated with this root node. Then it looks for properties, and there's a property called left. And when I reference the dot operator in left, again, it's a memory location. So we're just constantly looking up a blob of data, looking for a property that holds a memory location, going and getting that thing at that memory location, then looking for properties on it if it has one of this name, right? So it is just a repeated process here. But that's how this works. There are not multiple values stored in memory for each node. So despite there being different ways for me to access this value, there's still only one blob of binary data representing each one of these nodes, right? So we have 4 total nodes. Despite there being lots of different ways to access them using the dot operators, there's only 4 nodes in terms of binary in memory stored. All right, so that is important to keep in your mind. All right, so we can run this one more time. All right, and we see that also referenced that last item 3. Okay, so I was talking about the print node tree, and there's a couple things we need in order to get this to work. One of which is we have to be able to use the length function. So any method that you define here that starts with underscore underscore, these are generally predefined Python methods. And what this one in particular allows you to do, it allows you to use the len function. So what does it mean to call, if I have a tree down here, I have tree, what does it mean to call something like print the length of my tree? I might add a little label here so things don't get too messy. So if I use the len function and I pass in a tree, what does that mean? Well, what we want that to mean is we want it to return the length property here. We want it to return the number of nodes in our tree. So we'll return self.length. Okay, and again, this is built in. All this really does is it allows us to use the length function with one of our trees. All right, so if I run this, now we see there's 4 nodes in our tree, so the length of our tree is 4. And we got to use the standard syntax in Python to calculate the length of something is the len function. Okay, so that's nice. We got to use that. What else do we need? We saw that we needed to use a get function. So in the other version, we would just reference by square brackets and pass in the index. Here we have to get something by an index value, right? And again, we have to remember to put self in there first. All right, so what we can do to start with is we can say if index equals 0, return self.root.value. Elif, sorry, that should be double equals, we're comparing something. Elif index equals 1, return self.root.left.value. And then I'll copy this and say if index equals 2, that's going to be self.root.right. And then I'll copy this one. If index equals 3, self.root.left.left.value. Okay, so this will take care of all 4 of our nodes. So it's going to get the value of a node by a particular index. We can see there's an obvious shortcoming here as the tree grows, right? Well, this is unsustainable, right? We can do this when we have 4 nodes, but if I have to add an elif statement each time, there's a clear problem with how I'm decided to implement this, right? So we're going to fix this later, but this is the simplest way to sort of do this and get the print node tree idea working. All right, so let's see if we can call print node tree and pass in tree. Okay, so it worked. Now this is kind of held together with duct tape and glue and maybe a few nails, right? This is not necessarily well built yet, but we can see that we have correctly wired our tree up together, right? So the initial root node is 0, its left child is 1, the right child is 2, and then left is 3, right? And we see again the levels here. So what's the next thing we want to do? What do we want to do? We want to probably try to think of a better way to get an item. All right, what's a sustainable way of getting an item? So let's just delete all this and think this through. All right. So first of all, what are our edge cases? What are our out of bounds cases? If index is if self.length is equal to 0, then we don't have any items to get. You can't possibly get anything. Or if index is greater than or equal to self.length. Right? Or we could also say or if index is less than 0. Right? All of those would be invalid cases. Right? If the index value is less than 0, that can't be possible. We're not implementing negative indexing like Python lists do. We could, but we're not going to for this. If the index value is greater than the length, then that's not a valid index, right? And if we don't have any items at all, right, then you can't possibly call get and get anything to be returned. So we're just going to return nothing. So a return, blank return statement by itself, or a keyword return by itself returns none. That's the same as saying return none. Right, so we're just going to leave that none part out. But this takes care of our sort of edge cases, our out of bounds cases. Now we need to think about how we want to get something by index using this sort of tree structure, right? We don't have the benefit of the Python list where we can just access something by an index number. So what we can do, though, is we can create a visitation queue. So I can visit this node, and remember, a queue is just a line. The first item in a queue is the first item out of a queue. In Britain, they commonly call lines queues. You're waiting in line, right? In America, we tend to say, well, I'm waiting in line for something. I'm waiting in line at the bank. I'm in the queue at the bank, right? But queue just means it's the same idea as a line. You're waiting in line for something. So you enter the back of the line, and then you exit the front of the line. So you are added to the line at a different side than the side that you exit the line. Okay, that's the important bit. So you add things to the opposite side from which you remove things. So that's really what a queue is. And we can have a visitation queue. So when I visit a node, I'm going to add it to the queue, put it in the line. And then I will pop an item off of that queue and check to see if it has a left child and a right child. And if it does have a left child, I will add the left child to the queue. And then if it has a right child, I'll add the right child to the queue. And then I will pop off the next item in line, which would be 1. And I will add its children to the queue, 3 and 4, keeping in mind 2 is still in line. Right? So then I've added these 2 children to the queue. Then I look in my queue, what's next? 2 and 3, well, I add 5 to the queue if it's there, the left child, and I add 6, the right child, to the queue, keeping in mind 3 and 4 are still in line. Right? So we can see using this queue, we can sort of add things to the line in this sort of breadth first fashion. And if we can do that, then at some point the index is going to match how many items we've added to the queue. So we have to keep track of that. How many things have we added to the queue? And once index matches that, then we know that's the node we're talking about. Okay, so let's take a look at that and see what that means exactly. All right, so first we make this visitation queue, visit queue, and again this is just a line. This visit queue, and we're going to start out with self.root as the beginning node. Now remember, if we don't have any items, so self.root would be none if the length was 0, we've already returned. So at this point we know we have a valid index, and we know that we do have something stored in root. Assuming there's no other problems with our logic. Okay, so and then I will be our counter, right? This is going to count how many times we've added something to our visitation queue. Right? If we look at bin tree, I'm going to have this I value start at 0, and then as soon as I add something here to the visitation queue, I'm going to add 1 to our visitation queue, or add 1 to our counter. Right? So as soon as we visit 0, then we're going to add 1 to our counter I. And then as soon as we visit 1, we're going to add 1 to our counter I. We visit 2. So this keeps track. I is keeping track of where we're visiting, because eventually we need to stop at one of these nodes and find out, we need to return the value at this node. So we need to find out if our counter matches the index number, then we know we're on the right node. So we'll start I at 0, and then we'll say while I does not equal index. We're going to go through this loop. And I'm going to pass on this implementation right now. So this loop is basically going to increment I over and over until it matches index. And the whole point of this is at that point in our queue, the thing at the very beginning of the queue is going to be the node we're looking for. Okay, so after I do this loop, the thing at the very beginning of the queue is going to be the node we're looking for. So in that case, we would return visit queue dot pop, and we're going to pop off the first item. Now remember, this is a queue, so we're going to add items to the end with append, and we have to remove items from the opposite side. Right? So we can toss something in there. We can say remove from opposite side of add. Okay, so we would visit queue.pop. This gives us the node in question, but get is not supposed to return a node, it's supposed to return a value. So we say dot value. All right, so if we look at this, let's say the simplest example, we know we have self.root, and let's say we're looking for the item at index 0. Well, if we're looking for the item at index 0, does 0, is that not equal to 0? So the index we're looking for is 0. This is false, so we don't have to do anything in this while loop. And then we pop off the node in our visit queue, which is root, and then we get the value. Okay, so at least for the very first node, this seems to work. Now, what if index is 1? Well, now we need to start adding items to our visit queue, right? So we use this node variable, and we're going to say node equals visit queue dot pop 0. So that's going to pop out that first item. Right now, initially, it's just the root node, and there's nothing left in the visit queue, but that's okay because we're going to add more things to it. So the reason we pop this off is because we need to check to see the left and right values. We want to check to see we've popped off the root node, and we need to check the left and right values, and we're going to add them to that visit queue. And then we're going to iterate through the loop again and pop the next one off the visit queue and add its children to the visit queue. So after 1, there will be 2, 3, and 4 in the visit queue. Then the next item in the visit queue is 2, so we pop that off, and we add 5 and 6. So at this point, then we'd have 3, 4, 5, and 6 in the visit queue. Then we would pop off 3 and add 7 and 8. We would have 4, 5, 6, 7, and 8 in the visit queue. And we would just keep doing this until we get to the appropriate node. All right, so we pop off the first node, and we say if there is a node dot left, so if node dot left exists, then we're going to go ahead and append that to the visit queue. And then if node dot right exists, and this is equivalent to saying if node dot right does not equal none. Right, same for node dot left. It's just shorthand for that. So if node dot right exists, we're going to say visit queue dot append node dot right. All right, and then the last thing we have to do is we need to increment this I every time we visit a node. So everything in this while loop represents a node visitation, right? So we pop off a node and we're visiting that node. And then we're adding its left child and its right child to the visit queue. But part of visiting a node is adding 1 to our counter. So I is going to equal what it did plus 1. And then at some point, I is going to equal the index that we're looking for. right? So if we're looking for the index 1, right, we pop off the root item that's stored in node. Node.left does exist. That's the left child, right? So visit queue.append left. Node.right does not exist, so we skip over this, and we add 1. Does 1 not equal 1? This becomes false, and that means when we pop off the beginning item of the list, that's the node we're looking for. Okay, so this is much more complicated than the initial attempt at get, but the initial attempt at get was completely unsustainable. The more items we add, we would have to add a line to support a certain number of nodes in our tree, right? This works with any number of nodes. Okay, so this idea is very important in computer science. You want to try to code things up that that aren't limited by a particular number. You want to code things up that scale. So if I can make an algorithm for sorting 10 things, I want to make sure my argument my algorithm can sort 100 things or 1,000 things or even 1,000,000 things, right? You want algorithms that scale easily without you having to add code. All right, so this get implementation, let's take a look and see if it works. If we did this right, we should be able to run the program again and nothing will have changed, but get will work in this new way, and we should be able to add some items to it. So let's run this, and sure enough, it worked in the same way. So that's not necessarily that exciting until we start adding new items, right? So now we can add a whole bunch of items, and we need to figure out a way to add items to our tree without having to manually wire them up like this. Right? This is not the way this should work. I should be able to have a function down here called add, and this is going to take in a value, and I could add something to the end of my tree. Now, where do we want that item to be added? So we're going to follow the methodology we use for bin tree list, where we add things in a complete tree fashion, where we go layer by layer, and on each layer we go left to right. So like this order. So if I were to add an item to this binary tree, it would go as a right child to number 11. Okay. So the trick with this one is we're going to be sort of doing the same thing we did with get, but instead of looping until we find something that matches the index, we're going to loop until we find a node that doesn't have a left child or a right child. So we check the left child. If it exists, we move on and we check the right child. If the right child is none, then that means that's where we're going to add the node. And this is entirely dependent on our existing binary tree structure. We know the way we're creating this binary tree, it's not possible to have no left node and a right node. And that's a restriction on how we're creating this binary tree. There's lots of binary trees that can exist like that, but strictly speaking, how we've decided to construct this particular binary tree, we know that to be the case, and so that's how we can look. So we can basically scan every single node, check their children, and if their children exist, move on to the next node. Children exist, move on to the next node. Children exist, move on to the next node. Children exist, and you check the left child. That exists, move on to the next child, and then here. This is where it's going to add. So this is going to be very similar code to the get function we just did. So let's see what we can do here. We're going to have first a new node, and we're just going to create a node from our value. All right, if self.root equals none, then that obviously means we have no nodes in our tree. So I'm going to say self.root equals new node. And then we're also going to have to keep track of that length property. So self.length plus equals 1. All right, so if that's the case, if we're adding the very first node in the tree, and then self.root is going to be none, so this will be true, and we're just going to set root equal to that new node, and then add 1, and we're done. And we would just return from the function. So this was the root case is a special case because the tree actually has a root property. All the other connections in the tree revolve around the nodes connecting to each other, right? Not the tree. So there's a special case in the tree class that if there are no items, right, we do have to set that very first node to root. All right, so that's what we did there. What's the next step? Well, we're going to use this idea of a visit queue again. And we're going to put self.root in here. And you know, this assumes that we already have a tree that's wired up correctly. If you give it a tree that's not wired up correctly, this might fail. But if we always use this add, then it should always be wired up correctly, assuming this add function works. All right, so we have visit queue, and we're going to do a similar thing. We're going to use a while loop, and we're going to say as long as there are items in the visit queue, so while length of visit queue, we're going to get a node, and we're going to say visit queue.pop0. So this is all basically what we did in the get function, right? Except we changed this. Right? We could also say just while true, basically. We're trying to iterate through all of the items and find one where a child is missing, and then we're going to attach the new node to that empty child location. Right? So we just need a while loop that will continue, and we're going to end up breaking the loop anyway. So we pop off a node, and basically we check to see if it has a child. If node.left exists, right, then we are just going to attach the, or we're going to add this node to our visit queue, just like we did up here. If node.left exists, visit queue append node.left. Otherwise, we know that we have an empty child situation, right? So we will say node.left. We're going to set that equal to our new node because we know it's empty, right? If it's not empty, we add it to our node queue and we keep looking, right? If it is empty, we found our goal. We found the empty child location, and we're going to set that to our new node. We're going to say self.length plus equals 1, and then we'll just return from our add function, right? This effectively breaks us out of the loop. Okay, so even though there will still be more items in this while loop, when you have a return inside of a while loop that's inside of a function, this is effectively breaking out of the loop and then returning. Okay. Okay, so if there was a left child, then we added it to the queue, and then we check to see if there's a right child. If node.right exists, then we add that to the visit queue. Visit queue dot append node.right. Now, if that doesn't exist, then it's the same situation as we had here above. We know this is the empty child location. Else node.right equals new node self.length plus equals 1, and then return. And that's really all there is to add. So if you break it down like that, there's not a ton going on. The hardest part is understanding how visit queue works. and it's good to have a sort of visualization like this where you add this to the visit queue, pop it off, so the visit queue is empty, and then we check for the left. If there's there, we add it to the visit queue. Check the right, is it there? We add it to the visit queue. So the visit queue has 1 and 2 in it now. We move on. The next iteration of the loop, we pop off an item from the visit queue, so the visit queue has 2 in it. And then we add 3 and then 4. We move on and pop off 2, we add 5 and then 6. We pop off 3 and add 7 and 8. Pop off 4, 9 and 10, pop off 5, 11. Right? So that's the whole idea. That gives us this sort of breadth first navigation strategy. All right, so we can, if we look at our code, we can change how we're wiring all this stuff up. We can say, instead of wiring these up manually and printing all this stuff out, we're just going to create a tree. We're not setting the tree stuff manually. In fact, we can get rid of everything except creating the tree, and then we'll make a for loop. For I in range, however many items we want to add. So we'll say 15. We're going to say tree.add I, and then we'll print out our tree. And so we get this nice structure, and this matches the structure that we had in the other one, in our other binary tree list example. So now we just need to do the traversals, right? So I will leave that exercise for next time. You can do the different traversals. Now that you have a way to get items, right, then theoretically everything you did in bin tree list, you should be able to get the items and print them out, right? So here this would be, instead of tree data index, you would say tree.get and then pass in index. The one that's going to be more difficult is breadth first traversal. Breadth first traversal, we can't as easily do that one. We could use, well, I guess we could. Yeah, we could just use a for loop and use our tree.get again here. So that one actually would be easy too. You could also do it with a visitation queue if you wanted, right? But you can do all of these, the breadth first traversal, just the same, and the depth first traversals with this binary tree node structure that we've created ourselves. And sort of the whole point of this is to help you start understanding how data structures work. We use data structures all the time that are sort of built into our programming languages, but how do they work? If you're only allowed to use the most basic tools, how can these things work, right? So this has been an introduction to binary trees and tree traversals. So hopefully you learned something. I'll clean this code up again just a little bit, and we'll scan through it again so you can make sure everything matches. Hopefully you're working along, and we'll scan through this nice and slow. And here's the add function. And then our tree, and we can make one more change to make this match the output. 97 and 97 plus 15. Change that to character. So again, this might look like some magic to you, but that's because the ASCII number for the letter A is 97, and so if you pass in the ASCII number to the CHR function, that turns it into the character. So that's all we're doing. So we're going from 97 to 97 plus however many items we want, and we're converting that to a character and adding it to our tree. So now when we do this, we have the letters instead. So that sort of matches where we were with the last one. All right, that's binary trees. Hopefully you learned something. Thanks for watching.